is learning to play baseball for the first time. These are college team baseball players. They're all very skilled. How might we? Is there a way to actually even make their training more effective? Right, and so they had the players. They gave the players extra practice. Again, these are college baseball players, so they're already having their regular team practice, right? Obviously, and so they were given extra practice. And the extra practice, what was manipulated was whether they received 3 different kinds of pitches: fastballs, curveballs, and changeups. Whether it was blocked, so you would get like 15 of the one kind, and then the 15 of the next kind, and the 15 of the third kind, or they would be interleaved. So if you are the player, you don't know what's coming at you, right? And it could be randomly intermixed. And so let's take a look at the results. And of course, they had a pre-test at the beginning. It's always good practice, right? It's the same thing in your classroom. Always, you have 2 different groups. Do a pre-test just to make sure they're roughly around at the same point starting out. Right, so they did a pre-test. Yeah, generally they're around the same, slightly different, but roughly around here, right? You'll do about 13 or so solid hits, right? So that's a random pre-test. And then let's take a look at the block group. So the block group is the white triangle. So these are the ones that got 15 of the same kind of pitch thrown at the player, right? So that's block practice. And as you can see, their performance during practice, this is called acquisition, but that's actually another fancy word for training, right? So during acquisition or training, as you can see in the block group, right, their improvements, right, is the steep line going up, is actually good, right? It looks really nice, right? Block group is like doing very well, they're getting lots of good solid hits, blah, blah. Certainly looks better than the random group. The random group is in the black square, right? That's the one where it's interleaved, right? You don't know what kind of ball is being thrown at you. Right, so the interleaved group, they call random group here, during training, doesn't look as good. Right, if you go by performance during training, if you go by that. But of course, what's important to look at the test now, right? What happens during tests? And at tests, again, there are 2 conditions there. Random again means you do not know what kind of ball is going to be thrown at you. And then block was blocked, right? You would throw a certain number of the same kind and then move on to the next one and so on and so forth. What do we see happen at tests now? Right, there's now a switch over. Right? What looked good during practice now does not look so good during the test. Right? So if you look at the block group, the triangles, right, you're really high, good performance during practice, but now it flips over. Right? It's the random group that outperforms the block training group during tests. So that's, so we are seeing basically an effect of interleaving here. The block group looked good during practice, but because practice is not what counts, right? If you're playing an actual baseball game, you don't know what kind of balls will be thrown at you, right? So it's what counts is really what happens on the test, right? And here it's very clear, it's the random practice group that had the greatest improvement in performance, batting performance, right? And also they had a control group that didn't have the extra practice. Remember, these are baseball players that are training on their own anyhow. Right, and so that's the control group without the extra batting practice. But nonetheless, important, it tells us, right, that something that looks good during training may sometimes be illusory, right, may not actually last outside of the training context. So something to keep in mind as well. Okay, finally we're going to move this closer to home, right, more like classroom-based kind of topics. And we're going to end off with looking at interleaving effects in math learning. And this is work really spearheaded by Doug Aurora at the University of South Florida. There's a picture of him. And in fact, even some of the slides I'm going to use in the next following several slides actually just taken from Doug Aurora because he's done a lot of these presentations in the past. And if you think about math learning, right, we often think of it as problem solving, and math problem solving. And in order to solve a math problem successfully, it's not a trivial task, right? You need to select the right strategy. And that is not trivial, because if you think again, in the real world, on a final exam, the student is generally not told, okay, use this strategy to solve this problem. No, right? The problem is just presented to the child, to the student, and she has to figure it out. Okay, which of the dozen formulas or concepts I've learned about is applicable here? Right? In most cases, that's how exams are designed. But of course, because we want our students to know how, when and how, and it's appropriate to use certain strategies. Right? We don't want to just have to tell them exactly what to do at every step of the way. Right? So inferring the strategy is not trivial. And I'll give you an example. Let's just start with this one. Right? Simple algebra problem, right? The strategy for this one is straightforward. You rearrange the terms to solve for x, right? Move all the numbers to one side, the x on one side, and then you find out, okay, x equals to 1. Okay, straightforward enough. But not so straightforward for the student who's trying to grapple with this, right, for the first time, right? Because there may be problems that look alike superficially, appear very similar, but they maybe actually require quite different strategies, right? So I've just given you an example, on the left and on the right side, of such an instance, right? So the one on the left we've seen before on the previous screen, right? But look at the one on the right, right? Superficially very similar. X's, numbers equals 0. They all, right? If you don't look too carefully, you might even mistake the one on the left and the right as being equivalent, right? But if you know your math, you know actually for the one on the right, it's a very different strategy in order to solve. And then what compounds the problem is there are even cases where problems that don't look alike actually require the same underlying strategy. Right, let's take a look at this problem. Right, it's a word problem of a bird flying a certain number of miles east and then a certain number of miles north. And then, in order to figure out how far it is from its starting point, well, you have to use the Pythagorean theorem, right? And then calculate the length of the hypotenuse, whatever that is. And if you look at the problem on the right, very different, right, in terms of appearance, the one on the left. But in order to solve that problem on the right, it's the same strategy, right? We have to use the Pythagorean theorem. Right, so choosing the right strategy, the appropriate strategy, is not a trivial task for a student. And it doesn't just, apply to students at the lower levels. Even if you start moving higher and higher up in math, same issues apply, right? So we just talked about this example here. If you go a little bit more advanced in terms of calculus, right? Same thing here. You've got very similar looking kinds of problems, but again, requiring very different strategies. You learn statistics again. If you're familiar with statistics, right? Again, the difference between an independent t-test versus a repeated measures t-test is quite a subtle difference. So people get confused and stuff like that. So again, right? This is not restricted to like middle school algebra or something. Okay, so let's dive into Rora's study. The one I'm going to be describing in detail is the precursor to the paper that you read. The 2015 study that you read is the one that came after. So this is sort of the precursor, the one that was published the year before. But a lot of, quite a few similarities, right? It's again done in a middle school math classroom, done in Tampa, Florida, where Doug is based. And also same thing, he manipulated the homework assignments. Right? Because Doug knew that he couldn't go into a classroom and expect the teachers to overhaul their teaching and say, I want you to teach exactly this way, to redo your lesson plans and the sequence. No. He basically told the teachers to carry on teaching as they normally did, right, based on their existing lesson plans and the kinds of resources they use and blah, blah. And he said, just allow me control over the homework assignments that you give out. Right? So that's all he manipulated, the homework assignments. Right? And what he manipulated was whether the homework assignments contain block practice or whether they contain interleave practice. Right, so block practice just meant each homework assignment was 12 problems long, right? So they were standardized across the semester, right? Each assignment, 12 problems. In block practice, all 12 of them would pertain to the most recently taught topic in class, right? So that would be block practice. And then in interleave practice, the first 4 problems would pertain to the most recently taught topic. The remaining 8 would come from previously taught topics. So that's where the interleaving comes from. You get a little mini block at top, and the remaining 8 are all interleaved. And this was manipulated within subjects, right? Within subjects is just a statistical term to refer to the fact that each student experienced both conditions, just with different topics, right? So if you think throughout semester, there could be a bunch of, I don't know how many topics were covered in math, right? For some students, it's, topics A was covered with block practice and topic B were interleaved, and for other students it was the other way around, right? Some students did block practice with topic B and then interleave practice with topic A, right? So everything was within subjects. Every student experienced both practice conditions, just with different topics in the class. So just to make it more concrete, right, this is an example of kind of assignment that Doug gave to the students. Right, so this is an interleaved practice assignment, right? So as I mentioned, the first 4 will be a mini block pertaining to the most recently taught topic. So imagine this is one that comes right after the students were taught about percentages, Right, so of course the first 4 have to do with percentages, right? So students do get some practice about the topic that they are learning right now. But then the remaining 8 questions, right, come from previous week's topics, right? So some of them are like division of fractions and exponents, I don't know, whatever, right? Graphs and stuff like that. So the important thing to note is that for the interleaved assignments, right, problems of different kinds, right? Numbers 5 to 12 here are all different kinds of problems. Problems of different kinds were interleaved, intermixed within the same assignment. And then problems of the same kind were spaced across different assignments, right? So it's not as if the student now gets shortchanged in terms of practice with percentages. No. They do get more practice on percentages. It's just that it appears on the subsequent assignments down the line, right? So they get 4 here, but there are 8 more that will recur on the subsequent assignments, right? So no one gets shortchanged on any topic. Everyone gets 12 practice problems pertaining to each topic. Just again, make it a bit more concrete in terms of procedure, right? This is an experiment that lasted 9 weeks during the practice phase, right? That entailed 10 different practice homework assignments. And then they gave them a 2-week delay, a retention interval of 2 weeks, and then there was a surprise test, right? Surprise because you don't want the students to do anything special to prepare for that test. Let's take a look at performance on the surprise test. Topics that the students had practiced in an interleaved fashion. Right? Performance was about double, almost double, that of topics that the students had engaged in block practice with. Right? It's a huge effect size, a huge whopping effect size. Right? Again, in the context of a classroom experiment, this is very impressive, right? Because classroom, as Nicole was mentioning earlier on, right? We don't have any control over, what students practice and how much homework they do, whether their parents give them extra assignments, who knows, right? All that stuff, or what questions the student may ask during the day, blah blah, right? So there's a lot of unknowns going on. So to have this very strong effect here is really quite impressive. So much so that the New York Times, the science writer Benedict Carey of the New York Times, actually, this study caught his eye and he decided to write about it, right? And you can see it's a bit small, but I'll read to you the first couple of lines, right? So the article starts with, the math students at Liberty Middle School were not happy, right? The 7th graders' homework was harder and more time-consuming at first. Many of the problems seemed stale. They were old from weeks ago or months ago. Proportions again, and solving them interrupted the flow of the students' current work. Right, and the teacher tries to explain it. The teacher says they were having to remember and to work on stuff they had learned previously, plus the new material, right, that they're trying to learn currently. Right, so they had to focus on several things instead of just one. And they had a quote from one of the 13-year-olds, students, right? She says, "It took some getting used to, that's for sure." Right? So kind of a little bit amusing kind of tone to, at least that's how this article started off. Right? But of course it goes on to talk about how the findings really have implications for how we should teach. Right? That it may seem a little out of the ordinary at first, maybe you may take a little bit of getting used to by teachers as well as by students, but then at the end of the day, of course, the ones who reap the benefits are the students, right? The ones, if you practice in an interleaved fashion, getting huge benefits relative to all your practices just blocked. So I'm going to summarize all this right now. I think we talked about how spacing can benefit category learning, but it's not so much maybe temporal spacing per se, at least with the paintings we talked about, but when the different examples or categories are interleaved, right? A, B, C, A, B, C. And the explanation for that is when we interleave, what we're basically doing is we're juxtaposing the different categories, right? And when we do that, we probably help the learner appreciate how the categories differ, which dimensions, which features we should look at and focus on in order to tell apart A from B, B from C. And we also talked about how, at least with math problem solving, right, interleaving can be very beneficial as well, right, during practice. Right? And of course, the reason for that is because when we want to solve a problem correctly, right, it is important to be able to distinguish among the different kinds of problems, right? Because a math student doesn't just learn one kind of problem, right? All across the school year, they're learning lots and lots and lots and lots of different topics, right? So they need to figure out what kind of strategy is appropriate when. And so just knowing how to execute a strategy is not sufficient. first need to identify, if you get the word problem in front of you and you're the student, you're reading it, you need to figure out, from the word problem, and because the word problem is not going to tell you what strategies is needed, you need to identify from the features in the problem what kinds of concepts are relevant to this problem, right? So that you can then call upon the appropriate procedure or strategy. And if you think about that, that's exactly what block practice short circuits, right? If you give someone 10, 15 problems of the same kind, after doing number 2, 3, or 4, the student's not really thinking, oh, what kind of problem am I being faced with? What kind of strategy do I need to call upon to solve this problem? They're just repeating the same thing they did again and again and again, just so they can finish to whatever number 15 and hand it in to you, the teacher, right? So block practice really short circuits this step, and therefore also, hampers or the learning. Just to make it a little bit more concrete, screen, right? How does interleaving improve math problem solving? Right, so we talked about this one in quite a lot of detail, right? Things that look superficially similar, very confusable, right? When we interleave, we help discriminate between them and figure out, oh, actually this one, because it has the exponent here, it's quite different from this one here that doesn't have it, blah, blah. Right, we're better able to discriminate and tell apart similar looking things. But the other mechanism by which interleaving also helps problem solving is it strengthens the association between a given kind of problem, a given kind of category, and its associated strategy. Right? So once you figure out, I know what kind of problem this one on the left is, you then have to retrieve what the appropriate strategy is before you can execute it. Right? Or let's say if you were trying to figure out what kind of problem it is and you realize, oh, it's actually this one on the right, it's this class of problems. Then again, you have to retrieve the associated strategy and then execute it. Right? But again, we just talk about block practice. If you're doing 15 of the same kinds of problems again and again and again, there's no need to retrieve the appropriate strategy because there's only one strategy at play. You're just using the same strategy repeatedly back to back. Right? So you don't ever get to strengthen the association between a given category of problems and its associated strategy. So that's also bad, right, for long-term learning. So the practical implications, now back to you to think about in your classroom practice, the kinds of materials that you use to teach, whether it's worksheets, textbooks, whatever resources that you have, is practice usually blocked? Or is it already interleaved? Right? Some teachers say, oh, the way we teach pastoral learning, it's all interleaved already, blah, blah, right? So it's worth sort of stepping back and thinking and reflecting on your own practice, right? What is the default here for you? And here are some workbook examples that Dr. scanned in. These are actual kinds that that students actually use. It's for middle school math again. And as you can see from this example here, right, these are worksheets for Pythagorean theorem, and it's even labeled so, right? So they can, right there in front of you, it says Pythagorean theorem. And then there are like dozens of questions on the Pythagorean theorem. Right? So again, if you're a student and after you've gone through question number 4, you're really on autopilot, right? It's like, oh, the same thing, a squared plus b squared equals c squared, or whatever the theorem says, right? And there's really not much else going on, right? So there's something really to think about. Okay, some general conclusions. Hopefully I've convinced you that taking a test, right, can be a very powerful learning opportunity, right? Produces better long-term retention than just additional studying, additional re-exposure to the material, right? Generally, tests that involve more effortful retrieval, right, tend to be more effective. Of course, you want to maximize learning, couple it with feedback, with corrective feedback, right? Don't lose that learning opportunity. If you're going to review material that you're trying to learn, right? Review again means re-expose, not just for the first time, right? Repeat material. You should probably wait a while before each exposure, right? Space those review opportunities out, right? Because you get more bang for your buck. And also, I should point out that these are not mutually exclusive kinds of strategies, so you can always combine them, right? You can combine testing with spacing. You can have spaced retrieval practice, right? Retrieval practice can be a way to review. You don't just have to review using rereading the material. You can practice, test yourself, give yourself feedback. That can be a wonderful way to review as well. And then, most recently, we talked about how interleaving of the different categories, right, can improve category learning, right, primarily by facilitating what we call discriminated contrast, right? We figure out how to tell apart the confusable categories. Okay, I've come to the end of today's presentation. If any other questions, comments, feel free to let me know. Oh, good, just in time for the World Cup.
Thank you, Sean.